Good morning, everyone. We're going to pick back up this morning here in chapter 3. So we're in the middle of section 5 of chapter 3, and then this section's on the determination of formula from experimental data. And so we were just getting into the topic of sort of mass percentages are pieces of information you can get from experiments. So if we get information like a compound's comprised of 84.4% carbon and 15.6% hydrogen by mass, that's information that we can relatively easily get from different types of instruments that are available to us in the lab. And so from that information, the best we can do is work out an empirical formula. If you recall, we did an example before where two different compounds that had the same empirical formula would have the same percent by masses. So the best we can do with percent mass data is determine the simplest ratio of the elements in the compound. And so what we can do is try to determine, is it C1H1, C2H1, C1H2, so we can get the ratio of the number of carbon atoms to hydrogen atoms in the formula of the compound. So how can we do this? You might recall these problems, and a lot of ways problems are taught, I think in high school, say like assume a 100-gram sample. And I don't necessarily want to assume any sample. I just want to start with two masses that have this ratio. So I want to start with two masses for carbon and hydrogen that have the proper ratio of 84.4% carbon and the remainder 15.6% hydrogen by mass. So an easy way to do that without having to do any math is just to convert the percentages to grams, because this is what we really want you to see, is that's the mass of carbon that's going to be present within the sample in ratio to 15.6 grams of hydrogen. So we just want to start with two ratios of masses that have the proper percentages for the information given in the problem. By far the easiest way to do that is just to assume the percentages are grams. In other words, that you have that 100-gram sample. So you don't have to assume that there's a 100-gram sample. If you want to assume there's a 5-gram sample, you just have to do math. You have to take 5 grams times 84.6%, 5 grams times 15.6%, and work it out. So why do an extra math step when we can avoid it by so-called, quote-unquote, assuming a 100-gram sample? So assume whatever mass you want to assume, but just know that we're just trying to keep the ratio of the percentages intact, and that's going to be very easy just to assume those percentages are grams, and we keep the ratio intact very easily. And then if we have the mass ratio of carbon to hydrogen, wouldn't it make sense to get the mole ratio? Wouldn't it make sense to say, well, how many moles of carbon would there be within this particular amount of mass? So why don't I use the periodic table, look up the grams per mole for carbon. So I just got to go to the periodic table for carbon. And then we go to the periodic table for hydrogen, 1.008. And let's go ahead and calculate what those are. Now, I do get questions like, can you use 12 for carbon, 1 for hydrogen? I think in problems like this, sometimes they don't round perfectly unless you use the more precise number. So I just try to get in the habit of using 4 digits. And I bet most of you guys have started to already memorize carbon's 12.01 without even looking. So if you do enough examples, you start to memorize a lot of the more common atomic weights for like CHO, etc. So if I take 84.4, divide by 12.01, I get 7.03. I'll even write the extra digit, 7.027. Now that's still going to be in ratio. I like to keep the idea that this is the ratio to the amount of hydrogen in the sample. 15.6 divide by 1.008. I get 15.48. Now, do we want to round this to like C7H15? I don't think we do, because we're 15 almost a half. Doesn't really look quite like a whole, so I don't see one of them looks close to a whole number, but we're not close enough to whole numbers to round. I want to be within about 0.003, maybe 0.005 of whole numbers. So we want to kind of inspect here. We're within plus or minus about 0.00, not 00, about 0.03, maybe 0.05 at worst to round. You know what I mean? So like we can't round to 15, we can't round to 7. So let's do some math to try to find the simplest whole number ratio. So since we don't see whole numbers here, and most of the time you won't at this step here, so let's divide by the smallest. So divide by the smallest number of moles. Now, we have to divide them both by the same number, otherwise we break the ratio. So the key is that we have a ratio. And I can't divide one by 7, the other by 15. I got to divide them both by the same number to keep that ratio intact. So of course I'm going to get 1.00 moles of carbon. Now in ratio, to 2.20 moles of hydrogen. So still not close enough to round to 1 and 2. Okay, so I can't round this quite to 2. So I can't say it's CH2 in terms of my empirical formula. So then what do we do? Well, what I have to find is then the smallest whole number multiple. Well, why whole number? Well, if I multiply by a fraction, of course the 1 mole is going to be a fraction. So I have to think whole numbers. And so then it becomes a question of, well, let's start small. Let's double the 1 and the 2.2. So start thinking about multiplying the ratios. You got to multiply them both, of course, by the same number. Hopefully this doesn't break my screen like it did the other day. Then we go times 2 and see if we get whole numbers, and we don't. We're going to get 2 and 4.4. So that doesn't work. Then we go times 3. So we get 3 for carbon very easily, but then we get 6.6. So that doesn't work. What about 4? 8.8. Still not close enough to round. I think you see where we're going with this. We just have to keep going to the next number times 5. So carbon times 5 would be 5 moles of carbon. Now present in ratio to 2.2 times 5. I know it's 11, but I'm just making sure I don't screw up the basic math, but it's 11.0 moles of hydrogen. So again, we were looking for the smallest multiple that I could multiply those numbers by, making sure we see that we ended on 5. So my formula, my empirical formula becomes C5H11 from this data in this problem. Now, can we double check the mass percentage to make sure we didn't make a mistake? Sure, there's an easy check, right? We can just take 5 times the carbon mass, divide by the formula weight. So if I do 5 times 12.01 for the carbons, and then divide by the formula weight, so that'd be 5 times 12.01 plus 11 times 1.008. This just goes back to the mass percentages. That's 71.14 times 100%. So this is just my check to see that I get the proper carbon percentage. So 5 times 12.01 divided by 71.14 AMU times 100%. I get 84.4%. So checks out. So we can double check if we want to at the end of the problem just to make sure we're getting the right carbon percentage. Now there's other ways to solve the problem. Like you may look at this problem and has said, can I go through the equations a slightly different way to get at the formula? I'm sure there's probably 2 or 3 different ways, or maybe even more ways that we could have thought of putting this data together to solve the problem. But the general thought process, at least in my mind, is I go from mass ratios to mole ratios, which the mole ratios are going to be probably not on whole numbers, just unless the problem magically worked out with that 100-gram sample. Then I'm just going to find the smallest, divide by the smallest, and then if I don't have whole numbers, I just need to double, triple, quadruple until I find whole numbers. So in this case, we end at C5H11 for the simplest whole number ratio for carbon and hydrogen in this compound. Now, most like CH compounds are molecular in nature, 2 non-metallic elements. Most of the time, the empirical formula doesn't tell us anything. Like when the acetylene and benzene was the one example before, both shared the empirical formula CH. Sharing an empirical formula is really not special. There's really nothing all that exciting when two compounds share an empirical formula. What makes a molecular compound special or unique or have its properties has to do with its molecular formula and then its molecular structure. And so what we usually want to know about a molecule is its molecular formula, not necessarily its empirical. So how do we get the molecular formula? Well, so we're told here, like, it's just a second experiment. So we do a second experiment. So if the compound's determined to have a molecular weight of 142.3, so we do an experiment that furnishes the actual weight of the whole molecule, we can then work out its formula. Because the formula of the compound should have either one of the empirical units, and that's the molecular formula, should have two of them, three of them. So the formula has to have a whole number multiple of the empirical formula. It can't be a fraction because then we'd have a fractional number of one of the elements. So we have to have a whole number multiple of this empirical formula in the molecular formula. So what I want to do here to solve this out, to find the number of multiples of the formula in the molecular formula, is I just take the molecular formula, or the molecular weight, I'm sorry. So I take the molecular weight, divide it by the empirical weight. Let's call it an empirical formula weight. So the weight of the formula of the empirical compound, or the empirical formula. So in this case, C5H11's weight. So if I take 142.3, that's our molecular weight. And then I just divide it by that 71.14, the mass of 5 carbons and 11 hydrogens. I think you can see that that's going to be equal to 2. We can even just double check. I'm sure it's right dead on to 2. 42.3 divided by 71.14, 2.0002. So that's working out to the multiple of 2. And again, this should be really close. I mean, this should be within the 0.03 to be able to round. And then you shouldn't even need to then, like, this has to be a multiple. If it's not a multiple, we probably made a mistake on our empirical formula. So if you're doing a problem on a test, you have to find an empirical formula first, and then from that you have to find the molecular formula, and you find that this is like 2.5. Probably means go double check your empirical formula, go back through that problem again, double check it, fix it, come back, and probably get the right answer then. So this has to be a whole number multiple here. And so the whole number multiple would just be that we have C5H11 as our empirical formula. So the molecular formula just doubles both of these. So it should be C10H22. So our molecular formula would be that of a formula that could be decane. Like this looks like the molecular formula for C10H22, which was that C10 hydrocarbon we learned how to name previously. Okay, so this is how formulas can be determined from experimental data, is the idea. So that the formulas we have come to know, we can learn about through experiments that analyze the mass percentage of the elements in the compound to get an empirical formula. And then from there, we can get a second experiment, maybe a mass spec experiment, to get us the molecular weight. Now let's look at a second example that's more or less a very similar problem. Now when we have a metal here, chromium, carbon, and oxygen in the compound, this is going to probably look like an ionic compound. Now for ionic compounds, usually there's no molecular formula or molecular weight you need to know for an ionic compound. So for an ionic compound, usually what we want is that empirical formula. And so can we find the empirical formula for this compound here? Let me give a little bit of a thought on our starting point here. We also are told oxygen is the remainder because they all have to sum up, of course, to 100% mass. So if chromium's 36.6%, carbon's 12.7%, oxygen has to be the difference. So oxygen's percentage would just be 100% minus 36.6% minus 12.7%. So that remainder is 50.7%. Is the percent that's oxygen. And so then our problem would just begin with 36.6 grams of some mass of chromium that I can then relate to the mass of carbon. And then we're just running to the periodic table. Let me write chromiums. I don't know how many of you guys can even see it. That's 51, is that 52.00 to 4 sig figs? Oxygen 1600 grams per mole of oxygen. All right, so why don't you guys try to take it from here? Take a couple minutes to try to work out those mole ratios and see if you can come up with the simplest whole number ratio for these elements in this compound. In about a minute or two, I'll start writing two, and a couple minutes after that, go over the answer. All right, I don't know. I mean, there's a lot of number crunching this problem, so you may be in the midst of getting towards the answer, but what we're doing is converting to the moles of chromium, to the moles of carbon, to the moles of oxygen, identifying the smallest, which was the moles of chromium, which I've signified as X. So we're dividing all of these moles by 0.7038. So of course we get 1 mole of chromium in ratio to then 1.50 moles of carbon to 4.50 moles of oxygen. I can see that this is a 3-to-1 ratio. So that's looking like CO3 in the middle, so it looks like carbonate. But then to get these 0.5s to whole numbers, I need to double all of them. So that's going to take me to chromium 2, C3, and then O9, once I double all of them to get whole numbers. Now the C309, what that is going to look like, that doesn't look like CO3-3. So that's CO3-3. So that gives us our 9 carbons and our 3 carbons, and then our 2 chromiums. For answer D. So this is looking like chromium. Remember the charge, we don't have a whole lot of review on midterm 2, but that would be chromium 3+, or our 2- charged carbonate ion. So chromium 3 carbonate. So these types of experimentals, this data here is how we can determine formula. So you may be wondering, how did we ever determine the different formula for these different compounds? It's through experiments like this. Now these problems sometimes appear to be tricky, but I think it's just practice this a couple times. These problems are actually usually pretty straightforward because there's not a lot of different ways to give you the information, just the mass percentages to a formula. And then if you need extra data for the molecular formula for a molecular compound, then that would be like a second step. Let's go ahead and take our quiz here in the middle of class. Keyword today is halogen. All right, so most people are done playing on their devices mostly. Okay, so there's a problem at the end of section 3.5 that we're not going to discuss and cover. I want to mention and show you kind of basically what it looks like, just so if you see problems like this in the textbook, you can know that they're problems that we're not going to talk about. There are problems that give you the mass of carbon dioxide and water that are produced from a combustion reaction from a sample that combusted and perfectly, to 100% yield generated CO2 and water. These formulas or these problems would allow us to see how much carbon was in the sample from the CO2 mass, how much hydrogen was in the sample from the water mass. And then usually they have a third element you can determine by difference, kind of like we did the previous example with O. So usually you can do up to one other element that can be anything by simple difference. So you may see some problems that give you CO2 mass, water mass, and ask you to identify a formula. We should be, it's entirely within the realm of possibility to figure such a problem out, but we're not going to cover those or worry about those. They're a little bit long in length. Anytime we put a question like this on the exam, it's like a 5 to 10 minute question just for the one problem. So these problems have a lot of steps involved with them, so we're going to skip them in coverage and for exams. And just to show you what a problem looks like, again, this is the type of problem not to worry about. I think I've identified most of these on my daily quizzes. I don't think I've chosen any for the homeworks or for like the lecture examples. But if you see a problem telling you a certain amount of sample, usually in grams, and then massive CO2 and water, usually in grams, and then to determine a formula, that's a combustion analysis problem that you don't need to prepare for midterm 2 or for the final. Okay, so with that, that'll kind of take us into the final 2 sections in chapter 3, which are really on the key detail of chapter 3, which is stoichiometry, which is quantifying aspects of chemical reactions. This is really what we want to do. We want to just be able to understand what we mean by chemical reactions, what's implied through the coefficients and the subscripts. So of course, the subscripts are telling you how many atoms are connected. So I have H2 molecules connected together. That's what we mean by H2. But then the 2 out in front just signifies that we're going to have 2 molecules of H2. And then when we see an O2, we have two oxygens connected together into a molecule. So our reactants are two molecules of hydrogen, one molecule of O2 that they can react together, and then they produce by inserting an oxygen into either the two hydrogens to make two water molecules. So of course, we're not creating atoms or destroying atoms, we're just simply changing their form. We're breaking those hydrogen-hydrogen bonds, inserting oxygen bonds, making new bonds between the H and the O. And so we're making our new water molecules here. And the three-dimensional shapes, the structures, the properties, the energy associated with these reactions are topics for later. So many of the details of this reaction are for later. What's for this section is, how many molecules react together? If I take X number of molecules of hydrogen, how many molecules of O2 can react with them? How many molecules of water can be produced? Can we also talk about larger quantities? Because usually when we carry reactions out, we don't have a single molecule of O2, two single molecules of H2. We usually have a huge collection. So usually we have, masses of H and O that are reacting together, hydrogen and oxygen reacting together. So how many grams of oxygen can react with a certain amount of mass in hydrogen in grams? Or how many moles of the one can react with the other in the unit of moles? So the mole ratio is also implied by the coefficients, because 2 molecules times Avogadro's number would be 2 moles. 1 mole times Avogadro's number would be 1 mole. So the coefficients for molecules work the same for moles. So I can take 2 moles of hydrogen, react it with 1 mole of O2 to produce 2 moles of water. So I could look at the coefficients and see that it's the ratio of the moles of the reactants and products relative to each other that react and form in the reaction. I can then also convert using atomic weights and molar masses. So the molar mass of H2 is just 2.0 to 2 sig figs would be 2.0 grams per mole. That's H2. So if I have 2 moles of hydrogen, that would correspond to 4 grams. So 4 grams of hydrogen can perfectly react with about 32 grams of O2. The molar mass of O2 is 32.0 grams per mole. So if I have 1 mole, that's 32 grams. So I can take 4 grams of hydrogen, react it with 32 grams of oxygen, produce 36 grams of water. Why 36 grams? Well, in one way, because it's the sum of the 2 masses. We're not creating or destroying mass in the reaction, and we know the reaction's balanced, but also because water is 18.0 grams per mole. There's 2 moles of water, so 2 times 18.0 is 36.0. So then what do we do? What happens if we have 5 grams of hydrogen, but with 32 grams of oxygen? Can I react those together? Can I have one of the reactants in excess and one of them maybe not enough? Yes, that's like a topic of chapter 3 here, is that we can have an excess of one of the reactants and it should just be left over after the reaction completes. Most reactions will only react by the coefficients given. If we have too much of one, it's just left over after. We mentioned very specifically that combustion reactions are interesting, that if you have not enough O2, that you just never end up with the second O on carbon monoxide and you end up forming CO, carbon monoxide. So some reactions will change the nature of their products if you don't have enough of the reactants, but for the most part, our assumption is when we give you a reaction, you're assuming that that's the only reaction that can take place, and if you run out of one of the reactants, the reaction stops and the other one's just simply left over in excess. Okay, so that's meant to be just a quick intro. We're gonna walk through a bunch of type of problems here, and we're gonna kind of start with like a particle diagram representation so we can think about on a particle level what's going on, and then try to bridge towards larger scale, having more, larger quantities in moles and larger amounts of grams of reactants and products and how they can react together. Then also try to develop some tools to solve these problems in terms of, maybe using dimensional analysis, maybe setting up charts, and just trying to think about what's going on within these reactions. Particle diagrams, like this reaction here, is kind of nice because we can actually just kind of like sketch out what's going on with like pen and paper. Like the reaction here is showing us that we have nitrogen represented by the black spheres, oxygen represented by the gray spheres, reacting according to this reaction. So we have N2 plus 2 O2 go to 2 NO2s. And so if I were to take N2, one of them, and let's do 2 oxygens. Let me do these ones here. So I can like lasso out 1 N2, 2 O2s, and that they're going to react together. And then once they react together, I'm going to end up with an N with two O's. I'll just do the two O's open. And then another N, and then the two O's for my two NO2s. So now those are gone. They've now formed the two molecules of NO2. So I can do it again. So I can do another lassoing, and so I'm going to make another NO2, and then the second one. And they're not necessarily stuck together. These two NO2s can be anywhere in the box randomly, so they could be randomly oriented within the box. And then we can do it one more time. So I end up with an N, two O's, an N, and two O's. And then what about this guy? What about that last N2 that didn't have two O's to pair up with? Well, he's just here in the box. He's just left over as a excess reactant. So one way to find an excess reactant, one way to look at this box and find that nitrogen was present in excess and one molecule of nitrogen is left over once the reaction completes, is to just lasso out and draw a box and make a picture. This is nice when there's, a couple of molecules of each of them in the box, and we can do this. This isn't so nice if I give you an Avogadro's number quantity. Imagine doing this times 10 to the 23. Might take you a while. So, this is a perfectly good example for what we call a particle diagram problem for us to figure out that if the reaction proceeds to what we mean by 100% yield is that the reaction just completes, that we have every possible reactant combined together to make every possible product perfectly. When that happens, we form, if we count them up, 1, 2, 3, 4, 5, 6 molecules of NO2, and then we're left behind with the 1 N2 that's present in excess. So we should end up here with the 6 NO2s and the 1 N2 that's in excess. Now, are there other ways to find, out how many NO2s could have been made in this problem without resorting to drawing pictures? And the answer is yes, of course. And so how? Well, a few ways. One, I think, is just by inspecting the reaction. So if I'm just going to rewrite the reaction here. And then I'm going to write B for before. So before the reaction takes place, I'm just inspecting here that I had 4 NO2s. I'm going to write 4 molecules. And then for O2, I had 6, I believe. 1, 2, 3, 4, 5, 6. Yeah, we have 6 molecules of O2. Now, there's this chart called a BCA chart where we can then inspect the change. We don't have any initially before the reaction takes place. There was no NO2 in the box, so we might write a 0 in for the other reactant. But then the change has to go by the coefficients in the reaction. So for every X of N2 that I lose, for every one N2 that's lost, I have to lose 2 O2s. Then I have to gain plus 2X of the product. So I'm just looking at the coefficient in front for what I put in front of the X, and the negative is for loss, so we're losing the reactants, and then the gain is for the product. And so again, I'm just looking for the coefficients, what their numbers are, and then minus for the reactants, plus for the products. And then what this means, sometimes this is confusing, but it's for every N2 that I lose, I'm losing 2 O2s, and I'm gaining 2 of the product NO2s. And so then when the reaction completes, to go to 100% yield means that at least one of these is 0, but which one goes to 0? So that's the limiting reactant. The one that limits the amount of product that we make, or the one that hits 0, is our limiting reactant, and then the one that's left over is called the excess reactant. So now which of these is 0? Well, let's imagine we make a mistake, or maybe we're not sure. So maybe we think, well, if N2 is 0, can I solve for X? So if N2 is 0, if N2 is the limiting reactant, then our X would be equal to what? 4, right? So we have 4 minus X is equal to 0, and then X would have to be equal to 4. Just solving that is just a simple algebra problem. And so then if X is 4, 6 minus 2 times 4 would be negative 2. Now I can't have negative amounts, I can't go negative. That would be impossible. So I can't go negative in the amount of N2 that's left over. So then I can't produce 2 times 4, then I can't get to the 8 NO2s. So I just can't get there because we've ran out of one of the reactants. We've hit negative amounts. Okay, so what we would do in that case, if that's how we were solving this problem, is we'd go back and erase and then say, well, the other reactant must be the one that goes to 0. So the 6 minus 2x goes to 0. And then therefore, x would be 6 minus 2 times 3, so x would be 3 in order to make that work out. And so then 4 minus 3, keep turning the erase on, stupid pen. So 4 minus 3 would be 1 molecule of N2 left over, and then plus 2 times 3 would be 6 molecules of NO2 forming. So after the reaction completes, we've hit 0 with our O2, we have 1 N2 left over, and then we have our 6 molecules of NO2 that have formed. So we can set up one of these things we call a BCA chart. We'll set up a few more. A few things to think about here. One, that what I read into my B, the before, has to be either molecules or moles. So if we have grams or massive samples in grams, we want to convert those to moles or molecules here. So our B has to be either moles or molecules, because those are the reacting units of the reaction, not grams. So some problems might be well suited for a BCA chart, others not so much. I find you guys tend not to like BCA charts so much. They're a thought problem. They're like a thought example of solving a problem in my mind. They help me see that as the reaction proceeds, we're losing the reactants, gaining the products by their relative coefficients in the balanced chemical equation. Now, there's a third way. I hate to always start a problem off like this with multiple different ways to solve it. We can go particle diagram if it makes sense, if the numbers are small enough like this example, and draw a picture. We can use a BCA chart. But the third step, and the one that usually makes actual sense on why it works other than just through brute memorization, but the way to understand why it works is dimensional analysis. And you can apply like the BCA chart thought in this dimensional analysis step and hopefully understand how it works. If I want to apply dimensional analysis to solve this problem, it would just be to ask this maybe a simple question, like if I consume all of that N2 that's initially present and make as much product as possible, how much would I make? If I consume all the O2 that I have initially present, how much NO2 could I make? So I could ask the question, like, how many molecules of NO2 could I make if I consume all of the, let's start with the N2. And let me try to separate our attempts here. So we have attempt number 1 here, number 2 here for the BCA chart. So this is attempt number 3, just using math dimensional analysis. And so the first thing I'm going to do is see how many NO2s I can make if I consume all the N2. For every 1 molecule of N2 that reacts according to my balanced reaction, I produce 2 molecules of NO2. So that would be 8 molecules of NO2 if I consume all of the available nitrogen. And what about if I consume all of the, I zoomed out too much, my pen got bigger. Let me see if I can, whatever, it's no easy way to change it. Number of molecules of NO2. If I consume the 6 molecules of O2 that are initially present, and then their ratio is for every 2 molecules of O2 that are consumed, we produce 2 molecules of NO2. So I'm just looking at the ratio here for 2 to 2 in the balance equation. It says for every 2 O2 that react, we produce 2 molecules of NO2. So that would be 6 molecules of NO2. So we consume all the oxygen, we hit 6 molecules of NO2, we run out of oxygen. So at this point here, our O2 is gone. It's been fully converted to NO2. And then I can't get to the 8. So I can never get to 8 because I've ran out of all the oxygen when I hit 6 molecules of NO2. Now, dimensional analysis, I think, is the easier starting point for most problems. But you can see, if you don't understand the BCA chart, if you don't understand how a chemical reaction is working, it's just gobbledygook arithmetic that maybe doesn't mean a whole lot and that we can easily forget the concept. is just that we're just trying to say what's the most amount of product you can make off of each of the given reactants, and the one that's less is where we hit our stopping point. That's the most that we can make according to the amounts in the problem, and then the other reactants just left over in excess. And so then how can we solve by dimensional analysis the excess reactant problem? And so we can then say, well, the number of molecules of N2 that are needed to react with the 6 molecules of O2 would just be for every 2 molecules of O2 in the equation, it says I need 1 molecule of N2. So that'd be 3 molecules of N2 that react with the O2. And so the remaining N2 would be the 4 initial minus the 3 that react, leaving the 1 N2 behind. So we'll think through a couple problems, and this problem here is maybe so simple you don't need all these 3 options. If you're looking here saying, well, it's so obvious what the answer is, I could have just done it in my head, I can just do it on an easy particle diagram in my head without even writing it, I could have just looked at the question and looked at the choices and made sense of it without doing any of these approaches, and that's fine too. You know, like that just means you understand all of these solutions, and that's a good thing. And so when we look at more advanced problems, we look at problems that give you moles or different types of information, ask different types of questions. We can try to analyze which of these 3 options or 4 options, just doing it in our head, make the most sense, and then how can we really have the ability to use any one of those options depending on the particular question. Okay, so let's progress into just the general slide of what stoichiometry is it's just a mole-to-mole conversion using the coefficients in the balanced chemical equation. So when we do stoichiometry, we have to make sure the reactions are balanced. If we didn't properly balance the reaction, none of the math is ever going to work out right. And then we just use molar masses to convert between moles of like A and B. So the idea would be if you have like A going to 2B or something like this, for every A that reacts, we get 2 moles of B. If you know the molar mass of A, the molar mass of B, you can convert to the relative masses of A and B. So let's look at another example or 2 for today. So we have hydrogen and nitrogen forming ammonia. So we have to balance reactions. We can't forget, and really balancing reactions isn't hard, but usually what's hard is forgetting to balance the reaction. So what's easy to do is just to miss that we have to balance a problem like this. So 2 for NH3 gives us 2 N's on both sides. That gives me 6 hydrogens on the product side. So 3H2 would give me 3 times 2, 6 hydrogens on the reactant side. I can write the 1 in or leave it blank, but 1 and 2, so 3 to 1 to 2 here for the balancing of the formation of ammonia off the elements of hydrogen and nitrogen. So a couple questions here. Again, these at the molecular level, because the molecular level lets us just picture what's going on maybe a little bit more easily. But how many molecules of N2 are required to react with 6 molecules of H2? So if I have 6 H2, how many N2s do I need? This, usually you can do that in your head if you're saying 2. If you already said 2, that's great. Now, how can you show that with maybe dimensional analysis? Would just be very easily, we have 6 molecules of H2. Then we just use the coefficient for every 3 molecules of H2. We need 1 molecule of N2 to react with it according to the equation, so that would be 2 molecules of N2. I don't know if it makes sense to then do the BCA chart, but it's just like saying the BCA chart is just saying like 6 and then question mark, and then it's like a minus 3x to 0. So like you'd have minus 3x minus x. And if you're consuming all 6, what's your x equal to? 2. And so then we need this to be at least 2 so we can lose the 2 off of it to it also to go to 0. So I think the BCA chart here is a little bit confusing, to be honest. And it might make more sense in other problems. So if you were thinking BCA chart or how can we apply it, it's by just kind of saying, I know the H2 needs to go to 0. We can solve for x and then see what N2 had to be so it could also go to 0. Because you're wanting both the elements here, or both the reactants to react with each other perfectly and to consume each other. So then how many molecules of NH3 are formed when the 6 molecules of H2 reacts with as much N2 as required? So the number of molecules of NH3 would be equal to the 6 molecules of H2 that we initially have present. For every 3 molecules of H2, we produce 2 molecules of NH3. So again, I'm just looking at my balanced equation for the 3-to-2 ratio. And so that'll be 4 molecules of NH3. I won't go through the task of sketching a picture, but you can sketch a picture if you wanted to for this small quantity. So you can make a picture, make sense of it. So the idea would be within these simple, more particle level examples, can we at least picture what's going on in our minds or on paper if we have to, and then think about the reacting unit being either molecules or moles, in this case molecules, and then we'll bridge into an example more like this where it's more or less the same problem when we give you grams and mass of samples. So here we give you a reaction that's already balanced, but it's the glucose plus oxygen combusting to form CO2 and water, so a basic combustion reaction. We have 6 carbons on both sides, 12 hydrogens on both sides, and 6 plus 12, and then 12 plus 6. So we have 18 O's on both sides. So just making sure we have a balanced chemical reaction. And so we're asked here how much CO2 is produced in grams when 2.50 grams of glucose reacts. So how much product is made when a certain amount of quantity reacts. And so the assumption is that there's going to be enough oxygen. So like we're assuming that there has to be, in order for this to react to produce the CO2, there has to be an excess of oxygen, or at least enough oxygen for this reaction to take place. We could set up a BCA chart, but to me, this isn't a BCA chart problem. This to me is like it's just the dimensional analysis problem of starting from the 2.50 grams of the C6H12O6. We just need to go to moles to get into that molar unit. So I need to go grams to moles in order to get to my 1 mole of C6H12O6 will react to form 6 moles of CO2. So I just got to convert to moles to get into the proper converting unit to use the coefficients in the reaction. And so 12.01's carbon times 6, I'm just going to the periodic table, plus 12.01, or excuse me, 1.008 for hydrogen times 12, 16 times 6 for the O's. $180.16 grams per mole. So again, this is just coming from the periodic table, atomic weights times 6 times 12 times 6 for the CH and O. But I need to know to convert to that just because that's my conversion I need to do to be able to use for every 1 mole of glucose. Converts to 6 moles of CO2. Then we want the grams of CO2, so we just need to do one more step. 1 mole of CO2, just use its molar mass. 16.00 times 2 plus 12.01, that's 44.01 grams. So I get 3.66 grams. So that's how we can calculate how much of a product forms off a certain amount of reactant that reacts. If we want to produce 25 grams of the CO2, like let's say we say, well, if we want to get 25 grams of CO2 to be produced, how much of glucose had to have been reacted to form that quantity? So we can go back through more or less the other way in this problem to figure out, well, here we want to solve for the number of grams of the C6H12O6 that would produce that quantity. Well, we just do the same conversions to moles, so 44.01. Use the coefficient 6 moles of CO2. Present in ratio is formed from the reaction of 1 mole of C6H12O6. Same molar mass to go back to grams. Let me even just show in both of these problems, we're just canceling out our units. Same thing here. Again, like I mentioned this last time, a lot of times this is the problem where if you're not writing the moles of what in, you may get your mole conversions easily backwards. So we need to write our units out. We'll really catch most of our mistakes that way. It's 17.1 grams. Now, could we have thought BCA chart here? I think we could have. I think once we see an example or two that might be a little bit more suited for like a BCA chart, like the way we might have set this up for the first problem here, the 2.5 gram problem, would be that we have to put the moles in before. And that's probably why I don't automatically run to a BCA chart on this problem here, is because I really need to plug the moles in. So I'd have to be doing 2.5 divided by 180.16 to write that in here, but I'd want to put the number of moles initially present here, and then just minus x, and then plus 6. We have to have enough by excess. I mean, there's an excess of the O2, and then minus 6x off the O2 plus 6x of water. So my BCA chart here has a lot going on that doesn't have a whole lot to do with this problem, but I could set it up. I just have to do a little bit of math. So it's probably not a problem I run to a BCA chart to help solve. So as we continue, we'll get into more discussion on limiting versus excess reactants, yields, percent yields, and then we'll continue into more problems, more examples. So we'll get into more examples of some problems that are helpful with the BCA chart, and then many examples that are easily solved with dimensional analysis. So we'll stop here for today. Have a great weekend. Enjoy the bye week. See ya.
Thank you so much, Dr.
Have a great weekend.